Welcome to the channel. On this video we're going to discuss the very famous inequality, which is the arithmetic mean, geometric mean, and the harmonic mean. So what are those means? So recall that if we have n real numbers and all of them are positive, so the arithmetic mean, we call it an, and this n refers to how many numbers are there. There's the normal average, which is the sum of a1 up to an, and then divided by n. Okay, and the geometric mean. Okay, the geometric mean is the nth square root of the product of all these numbers. A1 times A2, blah blah blah, n. And the harmonic mean is n divided by the reciprocal of those numbers. 1 over A1 plus 1 over A2, and so on up to 1 over A sub n. Okay? And then we have a theorem which says that the arithmetic mean always greater or equal to the geometric mean and greater or equal to the harmonic mean. Okay? And we are going to prove this assertion that this statement is true. And in order to prove this, we're gonna use induction. Well, there are several methods of proving this inequality, but in this video we're gonna use the induction method. Okay, so the induction. So we're gonna use induction on the following lemma. So let a1, an are positive real numbers such that a1 times a2 times up to an equals to 1. Then the sum of a1 up to a sub n is greater or equal to n. Okay. So first of all, we need to establish the base case. Of course, the base case is very easy, because when n is equal to 1, the provided information is right away implies. So if a1 is equal to 1, then certainly a1 is greater or equal to 1. So for n equals 1, if a1 equals 1, then a1 greater or equal to 1. So the statement is true for n equals 1. Okay. So next we assume that, before we solve for the general case, we might want to play how we can use the induction hypothesis and the given condition, right? So let's say that we prove this statement for n equals 2. How we can also prove for n equals 3? So that's actually how people usually solve for general case. It is quite rare that somebody solve it in the entire general statement. So usually, even though this is the statement for very general n, in order to figure out how we proceed, usually we take for several small n at the beginning. Then when we figure out for smaller cases, then we try to solve it for the most general one. Okay, so let's say that let's say that for n equals 2, it is true, right? If n equals 2 is true, what does this say then? A1 times A2 equals 1 implies A1 plus A2 greater or equal to 2. Okay, so suppose we have the following statement and accept it as a correct statement. How we can proceed to show that, if A1, A2, A3 equals 1, then A1 plus A2 plus A3 is greater or equal to 3. So we need to somehow connect the dot between the true statement that we are given, which is whether this will be the induction hypothesis, and we want to show this. Okay, so this is the statement about two numbers, but here we have a statement about three numbers. Okay, so let's think how to make this into a statement about two numbers, or think about this as a statement about two numbers. So between these two statements, it is easier to consider this given equation as a statement about two numbers. So we will rewrite this as A1 times A2 times A3. Okay? So we can think of this as a product of two numbers, namely A1, that's the first number, and the second number is A2 times A3. Okay? So then, according to the induction hypothesis, by induction hypothesis, well, by maybe just say by n equals 2, then what we can imply? Then, according to this, if we have two numbers so that their product is equal to 1, then the sum of the two numbers is greater or equal to 2. So from this statement, we can infer that A1 times A2 times A1 plus A2 times A3 is greater or equal to 2. Okay, but this is not, we would like to prove, we want to prove this statement. Okay, so how to get around this? Then let's try rewrite this statement so that the following terms appears here. So let's just force it. So this is going to be A1 plus A2 A3 plus A2 plus A3 minus A2 A3, right? So you can see if we cancel this A2 times A3, we get back A1 plus A2 plus A3. And we know this guy is greater or equal to 2. So this is greater or equal to 2 plus A2 minus A3 minus plus A2 A3. Okay. Now we do some wishful thinking that if instead we can show that this guy, these three terms, the sum of them are greater or equal to 1, then we are able to show the statement that we want to prove, right? So then we can ask ourselves, is it true that this expression always greater or equal to 1? Okay, so let's do it here probably. So we ask ourselves whether this guy is always greater or equal to 1. Okay. Okay, let's move the 1 to the left hand side. Okay. And if you recognize this expression can be factored. Right, so we factor as 1 minus a2 times a3 minus 1. You can check. 1 times a3 is a3 here. 1 times -1 is -1. Minus a2 times a3 is minus a2 a3. And then minus a2 times -1 is plus a2. So that's exactly it. Okay? So is it always true that if the product of a1 times a2 times a3 is equal to 1, then this expression always greater or equal to 0? So how can we get this expression equal to 0? Well, we can get the product of the two to be non-negative if both of them non-negative, or, so this one happen if both of these two guys are positive or non-negative, or what? Or 1 minus a2 is non-positive and a3 minus 1 is also non-positive, right? But are these statements always true? So let's say we have a product of three numbers. Well, this a2 and a3 can be, for example, a2 can be 10, a3 can be 100, and then a1 is just the number, so that if we multiply the 3 we get 1, so 1 over 10 times 100. And we can see that this a2 and a3 violate this, because if a2 is 10, this is going to be negative, and if a3 is equal to 100, that's going to be positive, right? So the product of this 1 minus a2 times a3 minus 1 is not always non-negative, right? That's our first impression. But notice that a1, a2, and a3 we can rearrange. What I'm trying to say is that we can exchange the role of a1, a2, a3. We can permute them without because the statement is symmetry with respect to a1, a2, and a3, right? So if we permute a1, a2, a3, then we have exactly the same statement. So what I'm trying to say is that even though this a2 and a3 does not satisfy this requirement, but if we instead relabel this guy, so this is become our a2 instead, and this guy become our a1, then this guy is less than 1, right? Less than 1, which makes this positive, and that guy is bigger than 1, which makes that positive. So the product is also positive. Okay? So we can see that to make the proof works, we need to choose a2 to be the smallest among a1, a2, a3. So is it true that if we have, let's say, a1 less or equal to a2 less or equal to a3, okay? Since the product of the three is equal to 1, the smallest cannot be strictly less than, cannot be strictly bigger than 1, right? Why is that? If the smallest is strictly bigger than 1, then we have something like this. So then all of them strictly bigger than 1, hence their products is also strictly bigger than 1. Meanwhile, we have the condition that the product of the three is equal to 1. Okay? So then this cannot be happening. So therefore, a1 less or equal to 1. Okay? And by the same argument, this a3 cannot be strictly less than 1. Why? Because if the biggest is strictly less than 1, then the product of A1, A2, and A3 will be strictly less than 1 times 1 times 1, which is strictly less than 1, which is contradiction to the fact that their product is equal to 1. So therefore, this cannot be happening, therefore A3 is greater or equal to 1. So then if we think of this A2 as the smallest, so we should read this statement as saying that the smallest among the three numbers is less or equal to 1, and the biggest among the three numbers is greater than equal to 1. So therefore, if we take the A3 as the biggest one and A2 as the smallest one, this guy less than 1, so 1 minus A2 is positive, and that guy is greater than 1. So A3 minus 1 is also positive, non-negative, I mean. So therefore, their product is also non-negative. Okay? So that's how the proof works. Right? So now we can see how we can generalize this method into the most general case. Okay? So I think we are ready to prove it. Or probably before we discuss it together, maybe you want to try by yourself first. So please pause the video first for a moment and try by yourself. Okay? Okay. Give it a try. Okay. Let's discuss the proof together. Okay, so we have shown that for the base case, which is for n equals 1, the statement is correct. Okay, and assume the statement is true for n. And we will show that the statement is true as well for n plus 1. Now, for n plus 1, that a1, a2, an plus 1 positive, and their product is equal to 1. And remember before that we can make the argument works if we pick one of them to be the smallest among the others and the other one to be the largest among the others. So we can assume that A1 is the smallest and an plus 1 is the biggest one among all those n plus 1 numbers. Okay, so without loss of generality, we can assume that A1 is less or equal to A2, an plus 1. Okay, and in particular, by similar argument that we discussed earlier, the A1 have to be less or equal to 1, and the an plus 1 is greater or equal to 1. Right? Okay. Now notice by the induction hypothesis, okay, now we need to rewrite the given information as the statement about the product of n numbers. Why we do that? So that we can, using the induction hypothesis, since A2 an times an plus 1, A1 is equal to 1. So here we think of this product as the product of n numbers, namely a2, a3 up to an. There are how many of them? N minus 1 of them, and then we multiply by one more. So we can think of this as a product of n numbers. And according to the induction hypothesis, if we have n numbers such that their product is equal to 1, then the sum of these numbers, a2 plus a3 plus an plus an plus 1 a1 is greater or equal to n. That's what the induction hypothesis says, because we assume that the statement is true for n, meaning that if we have n numbers so that their product is equal to 1, then their sum is greater or equal to n. Okay? Now, we need to somehow use this fact to show that the sum from a1 up to an plus 1 is greater or equal to n plus 1. But we're gonna rewrite this guy as the sum of all of this. Okay, let's put in the bracket a2 plus an plus 1 and then we need to compensate this by removing this guy minus an plus 1 an, and then we need also probably I just put 1 here as well, plus 1, okay, minus this guy, and then we don't have an and an plus 1. Sorry, we don't have a1 and an plus 1 in here, because this is a2 up to an and that one. So we need to add back a1 and an plus 1, and then we need to subtract 1. Okay, let's check it again. So this one will be gone with this one, and that one will be gone with that one. So then at the end we have the sum from a2 up to an, and then plus a1 plus a sub n plus sub 1. So that's exactly this expression. Okay. But now this thing is greater or equal to n according to this fact, right? So this is greater or equal to n plus 1. This is n, and this is the 1. And then we have this guy, plus 1 minus a1 times an minus 1. Okay? You can check that the product of these two guys are exactly these 4 terms. Right? Okay? Now, since a1 is less or equal to 1, this guy is greater or equal to 0, and this guy, since this is an plus 1, a sub n plus 1, this is also greater or equal to 0. Therefore, let me put it here, this whole thing is greater or equal to n plus 1, right? So that's it. We have the lemma, right? The lemma says that if we have n positive real numbers so that their product is equal to 1, then their sum is greater or equal to n. Okay? So how this lemma helps us to prove the AM, GM, HM inequality? Okay? So let's prove the first part of the inequality, which says that the AM is greater or equal to GM. The arithmetic mean for n numbers is greater or equal to the geometric mean for n numbers. How are we gonna prove it? Okay. So given a1, an positive, consider a1 over square root and square root of the product, and then a2 over and square root of this, and so on, up to an. Okay. What we can see about these numbers, if we take the product of all these numbers, what we get? On the top we have the product of a1 times a2 times an, and on the bottom we have the same number, the n square root of this guy, but there are n of them, so it's going to be the n square root raised to the n power. So the nth root and the nth power will cancel each other. So on the bottom we also have a1 times a2 up to an. So therefore the product of these n numbers is equal to 1. Right? So therefore we can use the lemma. So you can say that since a1 over dot times an and square root of a1 is equal to 1, then by the lemma, we have that the sum of these n numbers must be greater or equal to n. So what that means is the sum of a1 over this nth root up to an is greater or equal to n. Okay? But this inequality is equivalent to, so if we multiply both sides with this n square root, we have a1 plus a2 plus an greater or equal to n times this. And then we just divide both sides by n, then we have the arithmetic mean on the left hand side and the geometric mean on the right hand side. So we have that. Right? Okay, now we prove the last part of the theorem, which is the geometric mean is greater or equal to the harmonic mean. Okay? And so this statement is equivalent to the statement that proof the Gn greater or equal to Hn is equivalent to the nth root of a1, a2, an is greater or equal to n divided by this. Right? Okay. Which is again equivalent to multiplied by 1 over a1 plus dot 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 plus 1 over an is greater or equal to n. Right? Now notice that this we have here sum of n numbers that entice us to use the arithmetic mean versus geometric mean. So since by the arithmetic mean always greater or equal to geometric mean, we have, since this, we have that 1 over a1 plus that plus 1 over an is greater or equal to what? N times square root and nth root of 1 over a1, 1 over a2, up to 1 over an. But this thing is exactly what? The nth root of a1, a2 up to an. Now it is clear that if we multiply this expression with the nth root of a1 up to an, we multiply this guy to the left hand side and also to the right hand side, we can get right away this statement. So their nth root will be cancel each other, right? Okay? So let's multiply both sides by this and down. Right? So if we multiply the left hand side with this guy, we exactly have this expression, and if we multiply the right hand side with this guy, we exactly have n. So that's all. Okay, so thank you very much for watching. If you liked the video, don't forget to subscribe, and please, if you have any idea what kind of video we should discuss in this channel, please shout in the comment. So write in the comment what is the topic that you want me to discuss. Okay, thank you for watching. See you again in the next video. Bye.